Welcome to Chapter 5, Integration, the Language of Accumulation, Section 5.1, Anti-Differentiation and the Indefinite Integral. So I say see the short overview on page 377 of our book for a quick introduction. I'm going to go there right now. So this is what I'm talking about. Let's just read this. In response to global concerns about rising oil prices and the impact of green production, the USDA predicts, farms in the US are producing agricultural crops for energy production. The USDA predicts that by the end of 2016, the US will produce 12 billion gallons of ethanol from corn and 700 million gallons from soybean oil. So this book is a couple of years old. At the same time, farms are producing corn and soybeans for the production of energy. An increase in quality of life associated with economic growth in developing countries is increasing the demand for food. So we need energy and we need food. By collecting and analyzing data, it is possible to construct functions that model worldwide demand for both energy and food. Once we have the functions, we can use them to answer two types of questions, one using only algebra, and another using integral calculus. Algebra would be a question like, what will be the worldwide demand for food and for energy in the year 2016? So kind of a snapshot. A calculus question would be, what will be the total accumulated worldwide demand for food and for energy for the years 2016 through 2020? So a little different, what's happening over time. In this section, we will work with integrals that represent accumulation, such as the social utility of consumption, defined by, and then here's our new notation that we're going to learn, the integral from 0 to a of a demand function d of x dx. This integral gives the accumulated value the public places on its consumption and can be used to answer the above calculus question. So that's in the introduction to our book. I'm going to go back to our notes now. So we'll come back to that question later, but for now, we're going to think backwards using what we know about derivatives. So, for example, we know that the derivative of x cubed is 3x squared. So an antiderivative of 3x squared is x cubed, basically going backwards. There are other antiderivatives, however. Consider the derivative of x cubed plus 5. That is also 3x squared. And the derivative of x cubed minus 4 is also 3x squared. And the derivative of x cubed plus any number is 3x squared. So we say that the antiderivative of 3x squared is going to be this most general case, x cubed plus any number. And in this way, we cover all the possibilities, the plus 5, the minus 4, the plus 0, all those. And here's our new notation. We write the integral of 3x squared dx equals x cubed plus 3. This is an example of an indefinite integral, another name for an antiderivative. The long S sign, which is actually short for sum, that sign is called the integral sign, and the 3x squared is called the integrand. And then there's no special name for the dx, or the dx is sometimes called the differential. We don't really use that word in our class. Okay. And so in general, if the derivative of some function, which often we label with a capital letter, capital F of x, if the derivative is lowercase f of x, then we can integrate back antiderivative, the result, the lowercase f of x, with the notation, integral sign and the dx around it. And we get back the original function, but we put this plus c to acknowledge that when we take the derivative of a constant, it disappears. We don't know if it was there or not. Okay, just takes a little getting used to. So here's our integration formulas, most of them, or all of them. We're going to work from our derivative formulas. So we know that the derivative of a constant times x is just that constant. So k is a number. Okay, so since the derivative of kx equals k, if we start with just the plain k and anti-derivative it, derivate it, we get back the kx plus a mystery c. And notice that when we take the derivative of a power, x to the n, we multiply and subtract 1. And so we're going to do the opposite of those things. We're going to add 1 and divide. Here's our formula for a power. You start with some sort of power. Look at this. We add 1 and we divide by that new power. Okay, so it's sort of doing the opposite kinds of things. And this rule has to be only for n not equal to -1, because think about that n plus 1. If we try to plug in a -1 in for n, we're going to end up dividing by 0. So that's a problem. So the power rule is only for powers not equal to -1. That's that power right there. And we have a rule for that down below. We'll come back to that. Our most recent rule was the exponential. The derivative of e to the x is e to the x. So guess what? When we integrate e to the x, we get e to the x and then plus an unknown constant. And then lastly, the derivative of natural log was 1 over x. So if you see a 1 over x inside of an integral, you're going to get back the natural log. And you might remember that these vertical lines mean the absolute value of x, which just says that has to be positive. The domain of natural log is only positive numbers, so this kind of ensures that. It's a technicality. I'm not going to worry about too much on your written homework, and the computer is somewhat flexible with it as well. All right, so that's those vertical lines. And just some reminders that we can rewrite 1 over x as x to the -1. So right there, that's the case for n equal to -1. If you integrate x to the -1, you don't get the power rule, you don't add 1 or anything, you get the natural log of x. Okay, so that's I would say probably that's one of the big tricky things in this new world we're going to be in. Everything else is fairly straightforward. And then we do have our usual ideas that if you have a constant multiplying an integral, it will just tag along, just like when you have that with a derivative. And we can integrate term by term, just like we can take the derivative term by term. That's what these last rules are. So let's get into some practice. I think, let's see, looking at the time. Actually, I think I'm going to pause this and come back for part 2 to do examples.